In physics, there are 4 types of fundamental interactions, also known as fundamental forces. These are gravitational, electromagnetic, strong and weak. In this video, our main focus is on gravitational interaction or force. It is the weakest of all the fundamental interactions but has infinite range. Electromagnetic interaction has also infinite range as gravitational but cancels at large distances as very large objects have no charges. So only gravity has an infinite range and it is attractive for all types of matter. Galileo Galilei first studied gravity scientifically. Galileo discovered through this experiment that ignoring air resistance, the objects fell with the same rate, proving his prediction true, while at the same time disproving Aristotle's theory of gravity, which states that objects fall at speed proportional to their mass. According to Newton, the force of gravity is always attractive, works instantaneously at a distance, and has an infinite range. Most importantly, it affects everything with mass, and has nothing to do with an object's charge or chemical composition. It acts between all bodies having mass, following the long-range inverse square type Newtonian law of gravitation, where m1 and m2 are two masses separated by a distance r and g is the gravitational constant. Newton said that gravity is a force due to mass and only mass responds to gravity. So, according to this theory, light should not be affected by gravity as light is massless, since light is made of photons that have zero mass. But we'll see that it's not true. The second problem with Newton's theory was that it described gravity as an instantaneous force of attraction between two massive objects. Consequently, if you move one of them, the other knows about the movement immediately due to the change in gravitation, irrespective of the distance between them. So, if our sun vanished, Earth will stop feeling its attraction immediately, which is also not true. Actually, Newton did not explain the mechanism of gravity properly. But, over the years, scientists in just about every discipline have tested Newton's laws of motion and found them to be amazingly predictive and reliable. After about 200 years, Albert Einstein said that gravity is not a force but is the result of curvature of space-time. This statement had changed science's perception of gravity. 10 years later, of the special theory of relativity, in 1915, Einstein included the effect of gravity to generalize this theory for all state of motion. Because special relativity applies only when everything moves with a constant velocity, as there are no forces or accelerations, Einstein became a legend after this discovery. Sadly, only 14.5% of viewers are subscribers of this channel. 85.5% are not. Subscribers help us significantly in growing. Subscribe if you are new to the channel, and if you are already a subscriber, please like and share our videos. Thank you. Light is a transverse, electromagnetic wave and does not have any mass. Light travels in a straight line. We know that gravity affects objects which have some mass, but light particles do not have any mass, so gravity cannot affect it directly. But from relativity theory, we know about the space-time continuum, which is affected by gravity. Greater is the mass of an object, stronger is its gravitational field, and greater is the gravitational field, greater is the space-time curved around it. Let's take a simple example to understand it in a better way. Imagine a sheet of rubber stretched out. Imagine that you put a heavy ball in the center of the sheet. The weight of the ball will bend the surface of the sheet close to it. This is a two-dimensional picture of what gravity does to space-time in 4 dimensions. Now send a little marble rolling from one side of the rubber sheet to the other. Instead of the marble taking a straight path, it will follow the contour of the sheet that is curved by the weight of the ball in the center. This is similar to how the gravitational field created by an object affects light. So even though light travels in a straight line, the straight path on which it was traveling is not straight anymore. The path is curved near massive objects, which not the bending of light but the warping of space-time itself. If you want to gather all of these concepts in a single book, then The Invisible Creation is the best choice for you. Do you know all the stars, planets, galaxies and other visible objects make up only about 4% of our universe? The other 96% is made of invisible stuff. We cannot see or detect them but know about their existence. This invisible area of the universe is explained in this book. This book will give you a transparent idea and knowledge about this deep part of our universe. The subject matter is presented in a simple way, step by step with sufficient illustrations. This book may be of interest to students, teachers, as well as general readers without a science background who are interested in astronomy. The purchase link is given in the description box and the I button in the upper right corner. Gravitational lensing allows for the observation of a source of light that is not directly observable. Instead, the light emitted by the source is bent around an obstructing object due to gravitational interactions with other mass distributed through space. The reason gravitational lensing occurs is that light is influenced by gravity. Light travels in a straight path, which can be influenced by gravitational fields produced by other masses along its path. In this way, a source of light that is not typically visible along a straight line path can be seen through a curved path. It follows Albert Einstein's general theory of relativity. There are three classes of gravitational lensing: strong lensing, weak lensing and microlensing. Strong lensing is the most visually stunning form of gravitational lensing. It requires an extremely massive object like galaxy clusters, partial arcs, full arcs or Einstein rings, and multiple images are all strong gravitational lensing features one can observe. Weak gravitational lensing occurs much more frequently than strong lensing. Lenses can be clusters, individual galaxies, or even large-scale structure in the universe. Microlensing is most common on the scale of the Milky Way galaxy. This can occur when background stars pass behind foreground stars. This phenomenon also happened around a supermassive black hole. The arcs and rings around the black hole are the light from distant galaxies being distorted by the gravity of the black hole. The amount of gravitational lensing is directly related to the foreground object's mass. Gravitational lensing was first observed in 1979, but Einstein had suspected its possibility in 1912. In this new Hubble image, two objects are clearly visible, shining brightly. When they were first discovered in 1979, they were thought to be separate objects. However, astronomers soon realized that these twins are a little too identical. They are close together, lie at the same distance from us, and have surprisingly similar properties. The reason they are so similar is not some bizarre coincidence. They are in fact the same object. These cosmic doppelgangers make up a double quasar known as QSO 0957 plus 561, also known as the twin quasar, which lies just under 9 billion light-years from Earth. Quasars are the intensely powerful centers of distant galaxies. So, why are we seeing this quasar twice, some 4 billion light-years from Earth, and directly in our line of sight, is the huge galaxy Ganguli 1. This galaxy was the first ever observed gravitational lens, an object with a mass so great that it can bend the light from objects lying behind it. This phenomenon not only allows us to see objects that would otherwise be too remote. In cases like this, it also allows us to see them twice over, along with the cluster of galaxies in which it resides. YGKOWG1 exerts an enormous gravitational force. This doesn't just affect the galaxy's shape, the stars that it forms, and the objects around it. It affects the very space it sits in, warping and bending the environment and producing bizarre effects, such as this quasar double image. This observation of gravitational lensing, the first of its kind, meant more than just the discovery of an impressive optical illusion allowing telescopes like Hubble to effectively see behind an intervening galaxy. It was evidence for Einstein's theory of general relativity. This theory had identified gravitational lensing as one of its only observable effects, but until this observation, No such lensing had been observed since the idea was first mooted in 1936. I'm hoping to go into further depth about this topic in one of our upcoming videos. Thank you. If you like this video, please like and share it. And don't forget to subscribe to this channel.